Donald Alexander Stewart Fraser was born in Toronto in 1925 and spent his early years in Stratford, Ontario. His father and both grandfathers were doctors, and his mother was a nurse. He went to school at St. Andrew's College in Aurora, north of Toronto, before entering the mathematics, physics, and chemistry program at the University of Toronto as an undergraduate. He specialized in mathematics in the upper years, and in his final year was a member of the winning team in the 1946 Putnam competition, standing among the top 5 competitors overall. For graduate studies, he went to Princeton University to study mathematics, became interested in statistics, and finished with a PhD writing in the area of multivariate analysis under the supervision of Samuel Wilkes. He returned to the University of Toronto as an assistant professor in mathematics in 1949 and has been associated with that university ever since. He's held visiting appointments at Princeton, Stanford, Copenhagen, Wisconsin, Hawaii, and Geneva. Following his nominal retirement from the University of Toronto, he was professor in the Department of Mathematics and Statistics at York University for several years. And as well, he's an adjunct professor and frequent visitor here at Waterloo. But in 1999, at the University of Toronto, he is still teaching and supervising graduate students. He is notable for his nurture of promising students and for his generosity and supportiveness to students of all abilities and backgrounds. Among his 46 PhD students are many university statisticians, and it can truly be said that he has had a profound influence on the way statistics is thought about and taught, particularly in Canadian universities. When the University of Toronto established a Department of Statistics in 1977, he served as its first chair. His major research achievements began with studies in nonparametrics, leading ultimately to the 1957 book on nonparametric methods in statistics. At the same time, his very strong interest in the foundations of statistics and unique insights into their mathematical expression led to the beginning of his path-breaking work in inference, with its many implications through the years for the analysis of uncertainty in the context of parametric models and their extensions. He's the author of several books, including The Structure of Inference in 1968 and Inference and Linear Models in 1979, and author and co-author of close to 200 papers. Professor Fraser's research and writing has been recognized with many honors from very early on. He was elected a Fellow of the Institute of Mathematical Statistics in 1954 and a Fellow of the International Statistical Institute and of the American Statistical Association in 1962. He was the first statistician to be named a Fellow of the Royal Society of Canada in 1967 and the first recipient of the Gold Medal of the Statistical Society of Canada, inaugurated in 1985. In 1990, he received the R.A. Fisher Award of the Committee of Presidents of Statistical Societies. We're proud to note that in 1992, he accepted an honorary Doctor of Mathematics degree from the University of Waterloo.
Thank you, Don, for agreeing to do this interview.
Thank you for...
Okay. To start with, could you tell us a bit about your family background and any early influences you might have had that stimulated your interest in science?
Very supportive parents, sort of non-restrictive environment, local schooling in Stratford, and meeting people that accepted mathematics or were interested in mathematics, encouraged. Stratford itself, after that, it was mostly elsewhere.
I see. What was St. Andrews like? You went to St. Andrews College before University of Toronto.
Was a residential at the time, which offered a lot of opportunities. The physical environment in Aurora area at that time was superb. The college was good. It opened up possibilities that probably weren't easily available in Stratford. It was a change of environment, which is always supportive and reinforcing.
Was there any particular aspect of the mathematics training that was important to you there?
Well, there was final years were split years, so you were present with the grade ahead, so you could listen to this and listen to that. And mathematics is something where you like to feel and solve and resolve problems, and so you had something that material that you never had any contact with before, and you could hear something on it in a question, and you worked lots of opportunity to work on new and different things, so it just kind of opened up naturally.
Were there any expectations you would become a doctor, given your family background?
No direct from my parents. In fact, I think they probably would urge otherwise, not feeling it was a good thing to follow in the footsteps, or maybe not feeling that there were enough opportunities in medicine. If anything, that was reinforced the opposite feeling that maybe I should be going into medicine, and that stayed with me right through till, into the graduate level. I took a master's at Toronto, but with overlapping with pre-meds, and medicine was open, but sort of mathematics, it was just sort of second nature, so chance to go to the States, and the choice among several was Princeton, which I think fitted well. It turned out that there was it was the birthplace of statistics in North America, sure. Recognized, so I think it wasn't going there to study statistics, it was more analysis. So.
Going back to St. Andrews, how did you make the decision to go to University of Toronto for your bachelor's degree?
Probably the opportunity scholarships, I think. Alternatives. My father had been at McGill in Edinburgh, and thinking of medicine, both of those were real alternatives. I guess I explored them, but somehow, I'm not sure. I guess there are things that were happening that you weren't consciously aware of.
I see. At the time at Toronto, there were Beattie and Weber and Robinson and Coxeter on faculty. Were any of these people particularly influential to you?
They were all in their own way. I mean, their styles are so different, Coxeter, Weber, and Beattie. There wasn't a lot of overlapping patterns. There were kind of discrete patterns in people's style and what they did in mathematics, and then you kind of had to put them together. Those were fun years. I don't think I was a very serious student. I remember taking notes and not knowing what was going on, and then springtime exams, you'd start digging through these and saying, wow, that was interesting. Why didn't I think of that at the time or stuff?
Were there any particular directions of mathematics that appealed to you as an undergraduate?
Well, algebraic things never settled easily on me, and sort of more analytic things. I remember Brouwer, who lectured in algebra and Galois theory, and at the time it didn't ring, and then later looking back, I guess he was so frustrated with the student class, he'd do the same thing over again from different points of view. So on in April, when you're trying to put this thing together, you go through something and, hey, we've done this before. And yes. So you thought, poor Brouwer, Brouwer, I think he was quite a long time at Harvard after leaving Toronto.
Yes.
And I saw him on a visit there, I think maybe in '64, and he remembered me from a long time back. It was just kind of a delight.
I see. How did you decide then to go on to Princeton for graduate school?
Scholarships again, I think, plus the close contact between some people at Toronto with Princeton. They'd feed back who might be interested in studying mathematics there, and the Princeton people would find out about them and approach them. So there was a kind of an old boys network that kind of contacted students.
What was the role of the Putnam exam in making your decision to go on to graduate studies in mathematics?
Oh, gee. I don't think I really seriously thought about the Putnam. It was something that came along one spring, and there was kind of a party that a number of us went to, and then in the morning of it, we had to return a car that was borrowed and got lost in the street, so came rushing into the exam late with a scratchy pen, and maybe kind of it went in without being prepared, and suddenly faced with these things, somehow the answers all snapped out. It just kind of, and then did that affect later on? I guess it reinforced the feeling that you could do mathematics, or, you know, the success feeds whatever, and plus it led to I think it assisted the Princeton possibility, and then there was a Harvard fellowship that opened up, I think, fairly directly because of the Princeton.
Do you remember how you felt at your success in the Putnam exam?
Nothing, no sort of sudden elation, like kind of comfort that, well, you felt at the time you were solving things, and then after you solved them, the fact that it meant something was sort of secondary. I mean, the thing was, like, you got some really challenging problems, and somehow the pieces went together, and you had the euphoria then, and then sort of afterwards it sort of...
it happened.
It happened.
Right. What were you thinking about studying when you went to Princeton? What was in your mind?
I went down there nominally for algebra and analysis because that was the direction I was being pointed toward. When I got down there, it kind of indicated that I was really going to maybe work in actuarial science, partly because I had some connection with summer work in life companies, but I think there was nothing in actuarial down there, and Wilkes and Tukey were probably influential in nudging or tempting one towards the probability statistics side. And then there was a really exciting background of Lefschetz, Artin, Steenrod, and there's just a vibrancy about the place which was tremendously reinforcing. I don't think in the sort of areas of mathematics where you need a large amount of structure that you picked up over time and then meticulously work on it, I would be very successful at sort of, you know, getting into something that's raw and new and challenging its own way. So it's probably good that I drifted laterally or whatever into probability and statistics and able to work there in an environment that was very open-ended, because, I mean, they were aware of Fisher and there was nothing negative about it, where in the environment there was a lot negative. And you're just sort of like free to pursue ideas with a lot of challenging things in the background. So there's a lot of freedom plus a lot of challenge.
How did you first encounter John Tukey?
He was, and of course he still is, the Wonder Boy. At that time there'd been a 200th bicentennial at Princeton, and he'd come from chemistry into mathematics. And at this bicentennial, I think it was a bicentennial, there are mathematicians from all over the world, and here he was, a sudden recent PhD, and he was dialoguing with all of these people on their own home base. And there's Zorn's lemma, and then there's a Tukey lemma that's closely related to that. So he's sort of like Abel in any area.
I see. You actually wrote your thesis for Sam Wilkes. How did that come about?
Well, Sam was call him the father figure in the statistics group, and organized the background, and I think he was influential in sort of like saying, you don't really want to go into actuarial and other things, you should study statistics. And I don't think in terms of people pushing me towards sort of the algebra and analysis, there wasn't any overt sort of pull in that direction. Maybe I was just a little bit aberrant in my style or something. I mean, you'd meet in the common room periodically for afternoon tea, and you'd have the big names all there. But I think it was just more that there was a sort of family spirit about that statistics group, which was really, really quite nice.
Well, you mentioned a drift towards statistics from other mathematical areas. How did that happen? Did it happen through courses or just talking, casual conversations?
Background to it being at Toronto. I'm not sure. Like, I've been headed for medicine, and then I was doing abstract math and stuff, and there was There was a course being given on, call it applied statistics, we'd call it that now. And so I sort of attended, I don't know why, probably because of the actuarial side. You had probability and some statistics that would be integral to that, perhaps more than you'd find for the actuarial people now, so that you had some sort of background.
Okay. What was life like at Princeton? Were you teaching there?
Half-time the first year, and then somehow or other at the end of the first year I had sort of, call it homesick or whatever, I was going to go back to Toronto teaching and they persuaded me to stay on, and part of that was full-time teaching with sort of like double the stipend.
Yeah. How were the students that you taught?
Some of them, well, there weren't a lot. There were the typical undergraduate who probably came from quite wealthy families or scholarship, and there'd be a quite substantial general awareness, and then there'd be some really good people. There's one undergraduate who attended a graduate class, and he was working on problems that Tukey would set up, and we'd wind up, I was sort of competing, or there'd be a bit of a challenge. Well, Mel's going to be working on this, I better give it some thought. So we'd come into this thing, and we typically always have sometimes different versions of it. That was Mel Pizikoff, and he got his degree in Princeton, a statistical thesis, and while he was an undergraduate, he was refereeing for the Institute for the Annals of Mathematical Statistics. Not only that, he was refereeing for Abraham Wald, who was the world leader in decision theory at that time. So here's an undergraduate, sort of an undergraduate graduate class, refereeing the leading author in a leading journal at the time. So I mean, that sort of thing you just don't see ordinarily. It's an anomaly. I'm not sure whether that would happen at Princeton now, but it was part of the math department, maybe the statistics group at that time.
What did you write on for your thesis?
Well, problem suggested by Sam, it was multivariate in nature. It was counting hit probabilities using normal distributions to simulate things. It was fairly routine, sort of somehow get a thesis done. I don't make any great contributions or attempts at contribution there.
I see. Once you were done the thesis and you decided to come back to Toronto in 1949, how did that decision come about?
Well, I'd sort of decided to come back maybe the year before that, and then I stayed for the sort of like full-time teaching appointment. So it was just sort of following through on something in motion. I don't think there was anything sudden at that point. Partly it was tied with getting married at the time, and so there was a little more structure in the tenure track, although I don't think anybody talked about tenure track at that time. I mean, the term didn't exist.
I see. How Toronto's for a long time had very strong ties with Princeton, and were you feeling those at the time when you first came to Toronto? I mean, over the years you've recommended various students go to Princeton, and you visited yourself in 1955. I was wondering if the ties were very strong.
There were ties. I don't know whether they'd be particularly in probability or statistics, more maybe Gilbert Robinson, and several people at Princeton that he kept close contact with, and so you always knew about what was happening at Princeton, or someone from Princeton would call up and find out who the Toronto students this year were.
I see.
It was sort of a very solid diffuse network on that.
What led to the 1955 visit?
It was an opportunity to visit for half a year, and I'm not sure how long that was premeditated, or it was sort of like half a year away from Toronto. And I traveled back and forth a fair bit. There were new people at Princeton. In the meantime, Frank Anscombe had come, different mathematicians. It wasn't going back there that I worked particularly with anyone at the time.
I see.
Sort of always sort of what's John up to, because John was always up to something new and different, and it was always kind of exciting. I think at that time I sort of tended something that John was doing, and it was sort of like going through a whole bunch of different things and there'd be students, some of them now quite famous, who'd be scratching their head, and I, with a little more experience with John and having been familiar with him for long, and you'd sort of be able to link it together that between this blackboard and that, where there's a few changes in notation and stuff, but they're idea rich. Like, it wasn't just material, it was being unfolded. It was being unfolded with very rich in ideas, and they weren't worked out ahead of time, a lot of them, but the links were there, so it was kind of exciting because you could sort of feel the reality of something connected with it, and so it was amorphous coming to form. It was that was always exciting.
Wonderful. What was the University of Toronto like when you went there in '49? I guess on faculty in statistics there was B.A. Griffith and Dan Delury.
Right, well, Griff, as everyone referred to him, had moved into statistics. Dan Delury had been there and had been kind of dismayed with the University Canadian support of statistics, so he'd gone off to VPI, Virginia Polytechnic Institute. So there really wasn't any kind of nucleus. The actuary is Mackenzie was still around, and Shepard and Bailey, so there was kind of an actuarial group which had some consulting on the outside, so there was something real. There were some numbers, and there was some good experience in the sense of, you had to calculate things, so complex calculations, deferred annuities and the rest of it, or pension fund evaluations, and you had to lay things out in an orderly fashion, which was very helpful to me. I think back now, because sometimes when I do calculations, I want to get through, you see what the end is, and then you lose things along the way, and that's the kind of thing that was few people get the benefit of, and it helped me a lot, and I should think along those lines a bit more, I think, at times. Save a few pitfalls.
What was the teaching like at Toronto in those days? I mean, eventually you wrote this sort of two introductory books, Statistics and Introduction in 1958 and Probability and Statistics, Theory and Applications in 1976. And presumably the first one, the 1958 book, came out of your teaching experiences at Toronto.
Yeah, sort of reorganizing or organizing material in a way that you felt comfortable with the ideas. In both cases, the second one was a much more comprehensive, maybe a little bit too encyclopedic. So it tied in with the teaching, and some of the other ideas came out of, call them fourth year or graduate courses, where there wasn't too tightly specified curriculum, so you could sort of do things that you like or follow up on problems somewhere. And at that time, I think about that time, Dave Brillinger was going through, and so he would be enthusiastic about things and dealing with issues or always fresh ideas, and you could try things out on them, and that was really kind of fun. That sort of thing really wouldn't happen so much in a tightly organized curriculum. And sort of both Toronto at that time and Princeton, the curriculum wasn't really tightly organized, and so there was freedom to kind of digress as.
I see. You were developing courses then as you went along?
Yeah, well, you'd always be developing something and then question whether you build on that or whether you think of different ways of doing it and starting again. Sort of like currently, I've sort of been trying to organize material on likelihood, so you can take somebody who's had some math stat and sort of lead them into likelihood. A lot of our theory, they go through undergraduate courses and they don't know anything about likelihood, and then if you do any kind of applications to the rest of it, there are lots of things you can do, but for most things, somewhere you need to know what likelihood is, and somehow it's staggering that this doesn't come early enough, so somehow to get something that introductory. I've tried a couple times, twice now, and the second time was a fairly reasonable copy of the first one, and then I think I'd just like to sort of push that aside and then sort of like try again, reform it. And
how do you think it's going? How do you think it's going, the approach?
The likelihood has to be there, so it's whether you can succeed in sort of pitching it at the right level to people's background and bringing them on without getting into all kinds of things that lead people astray, shall we say.
Are you optimistic?
Oh, yeah. Oh, well, yeah.
Sure.
Yeah, I mean, that's part of it.
Now, you've certainly had a strong impact on the subject through your encouragement of very talented undergraduates at Toronto, in addition to your 46 PhD students. Do you have any particular insights on sort of student recruitment or mentoring that you'd like to share?
There was a time when a lot of people coming into sort of graduate work in statistics would be moving laterally from math or up from a math program, and so they had kind of the tools that you need for a lot of things in statistics. I mean, there's some areas in statistics which are areas for using math, and maybe the statistics that gets developed there isn't really the statistics that's sensible or reasonable. It's sort of like mathematics being cast into statistics, but sort of in terms of statistical ideas, you do need math, and you need the insight into the problems and the rest of it. So having that kind of mathematics, I don't think that should be measure theory, for example. I think, measure theory has probably mixed things up more in kind of the general statistical thing than, remember way back when there's heavy emphasis on Borel sets and having your probability space. Somebody very well-known applied statistician, he said, well, I do these things and I don't know where these Borel sets are. And well, of course, you come from mathematics, Borel sets are obvious. They're predicated by intervals and the rest of it, but it made you stop and think,
How did the Department of Statistics at Toronto evolve? Can you sort of lay out your experiences from 49? When you went back to Toronto in 1949, were the mathematicians encouraging to statistics?
Well, the department, a lot of people with very different, like from analysis, algebra, and there was the actuarial group, and the actuarial group needed probability, and you needed statistics, and they needed computation, and so they somehow provided a nucleus. I came back nominally into actuarial, and somehow you just kind of express interest in statistics and you wind up teaching in statistics, and I sort of never moved away from it. So there were this solid group of actuarial people, and that provided kind of the core, and then statistics just grew, and the mathematics people were generally very supportive, and then didn't try to second guess the statistics people. They let them pretty well organize themselves without structure, so it was a very flexible, supportive environment for statistics, and that prevailed for a long time. I've seen other places where the mathematicians want to participate in hiring and selecting, and their view of who it can lead a statistics department into be a department of probabilists or teaching only perhaps undergraduate, but this is where the statistics people were really providing the direction. Now that sort of separated at one point because Dave Andrews got a very large grant for a computer, and then the question is, where would this digital computer go? It needed air conditioning and the rest of it, and it produces a lot of stress within the department. The department didn't want a computer because that was violated what was viewed then as the purity of mathematics. Right now they have excellent computing facilities, and they have a whole office converted with the equipment in and air conditioning, so there was the initial resistance, and then they're sort of, well, their equipment is excellent. So the environment, and the separation more was into the first department of statistics was really a graduate department, and that was so that we could organize our graduate program, and that was really in our hands, statisticians, quite a separate from math. Mm-hmm. And then a year later, I guess the friction over the imminent computer led to the mathematicians wanting a computer and the statisticians needing the computer, so the split into separate departments just happened overnight. The dean said, fine, you decide it, and there was a bit of a tussle over the boundaries, and the dean just filled in the gaps the way you'd like to see it now, but never happens, so that suddenly there was a department, and then there were a lot of people who instead of having this big framework around it, were suddenly very much on their own. And so there were some interpersonal rivalries, power struggles and the rest of it, but that was short-lived. And
how many PhD students do you typically have at a time?
it's varied a lot. I think always more than one, maybe. It's sort of 5 or 6 now. Probably be up a bit in the fall. You can manage it if there's kind of areas that they get interested in as a rub-off from you, so that they work on different things and are mutually supportive. And I think that kind of student-to-student support is a fundamental thing, sort of, well, the educational process in general, and then getting into an advanced area where there's sort of a spirit of working with people and other people. And so when you come in and they start asking you questions, there's a good chance they've tried it out on themselves and have some new questions. So they've already got it part way along, and that aspect of, well, when NSERC applications, it gets into training of professional, and a lot of that is just this kind of environment where you get people working. And
do you have a standard schedule for new students who are working with you?
I probably should. No.
So it's sort of on a case-by-case basis.
Well, yeah, sort of like you hope they'll take off and pursue things, or you have to lead them, or then they get working too much on something that's too hard, and then that slows them down, and then you sort of see some of them that perhaps need more guidance to bring things together more quickly, or maybe they got hung up on computing when maybe computing isn't their forte. So
can we talk a bit about your own style of working?
Lack of style or whatever.
Sort of where and when are you most productive?
There's the pencil and paper where you have to kind of organize things, and then the definition of a problem, and then kind of feeling it, and then typically getting resolution. It's something that happens while you're doing other things. Or if you try to close in on it too quickly, then it kind of vanishes, or it becomes locked up in sort of technical details that aren't real. And so it's sort of something that happens. If you're I'm not saying I'm thinking about a problem now, but close to that sort of thing. If it's something in there, if there's a bit of a gap, you just have a little bit of imagery connected with that, and you can move pieces around without having like hard things in a piece of paper that tie it to something in time and space.
Mm-hmm. How many problems are you sort of carrying around at a time?
Well, I think it's a one-track mind, so it's usually one or another.
I see.
Then if you try to focus on too many, just by definition it breaks up and it doesn't work. So.
Okay. You also swim regularly, sort of late afternoons. Is that a time for thinking, or do you tend to turn off then?
The swimming ideally is sort of midday before eating whatever sandwich it is. Like somehow it's a break point in the day, and in the afternoon you kind of can start fresh. So I try to do that. It isn't always every day, partly because somehow that can break a day up particularly if you want to work, let's say, at home, and then it's half an hour each way, and then let's say a half hour swimming plus the other time, you've lost the middle quarter of the day. So some days I don't. It's not by choice. Then it's also a bit boring if you're going to swim a kilometer. It's 10 laps of the full pool or 20 of the half, and you kind of you start to think of other things, but then you start to lose count. But so you could be thinking of some problems there, or maybe other things. That just kind of pushes things apart midday, and you get a fresh look at things after.
I see. What kinds of problems have attracted you over your research career? Is there something that...
puzzling about why we do things. What's the structure of this? Does this mean sort of just how coming from the actuarial science, everything is well defined. You have probability background, but then you get into statistics, and one of the exposures is Well, what before, there was a book that was Uspensky, I think, that was being used, and it was actually getting things on the t-test and the power of the t-test, but it was in a mathematical context where you really didn't have a feeling for how this could be a part of an applied problem. Somehow the divide between the problem and the mathematics wasn't such that it reached into you when you were starting out in a career. Why is this being done, you know? And then the book Cremier was used at Princeton, and that had a lot of mathematics in it, mathematical statistics, and very good. Somehow he got into what's a random variable, and somehow the boundary between the repeated sampling and then the probability structure just didn't seem right, and it kind of, well, what is a random variable? Well, if you get the Kolmogorov, it's a function in a probability space, and that gets the probabilists off the hook because all the measure gets sorted out, but it isn't a realistic model, because if you're modeling things in statistics, where's this omega alpha p or whatever it is, some magic ultimate random process deep inside the earth, and then you get these realization, you're going to take another measurement on an animal or a human or a lifetime, and that's a function on that probability space. I mean, that's a lot of nonsense. And then you present this as the model, and then if somebody really wants to think about it, it doesn't make sense. I mean, it couldn't hold, it just couldn't be. But if you're building up a probability model, then you have this probability space, but where does it come in the final analysis? Well, you get all these variables that you're interested in, the product space for those, and the product algebra, and put the measure on based on finite base cylinders, and that produces the omega. The omega comes out from the outside, so why not start with the outside, which is where you usually start. You model this, you model that, you put them together by independence or by conditioning, and you build up your model, and there's no magic omega down that's producing all the randomness with a random variable as a function of probability space. I mean, I think most probabilists take that seriously. I think it's unreal, totally unreal. It solves the measure problem because the measure problem isn't there. You solve it ahead of time by defining it. But I mean, in the final analysis, it doesn't matter, but it matters in terms of people coming in terms of how they get oriented. I mean, if they get to think about that, then they're not thought of thinking in terms of building things up, which is how you build up models or define things with any structure.
How did you get interested in fiducial inference?
Well, I think there was a group at Princeton, Paul Meyer, Chicago was one of them, that read Fisher, and I think they had a weekly seminar where they read some Fisher. I wasn't part of that, but it was floating in the background, and so you'd read something in Fisher, and there's probably a bit in Kendall. Oh, that was the predecessor of Kendall, and Stuart Kendall on it, and so you come across it, and then it was part of conversation. I sort of got interested, and then you try to say, what's this all mean? What's the structure? How do you validate it? What's the frequency interpretation? And so that sort of led to the use of a group structure of models, and within the group framework, then quote everything's okay, and then when you get out of the group framework, then you have to maybe stop. As the fiducial, my current feeling is that certain of those ideas are appropriate in an approximate way that would materialize asymptotically. And in the asymptotic structure, you got to, if you're thinking of data incrementing and then you have models for the components, there's a certain asymptotic build up, and you have to accept what that structure is and what does it look like. And Taylor series, I guess I can thank you for getting caught in Taylor series expansion, because that's too algebraic for me, but it's necessary. And you kind of look at this thing, and then you see what the possibilities are, and the things that have been sitting around, like sufficiency. Sufficiency isn't there in that general context, but sufficiency is motherhood. I remember Dave Villinger saying he wanted to disprove sufficiency at one point. Challenging the really big things, and he went on to theses in other directions, but I think the thing about sufficiency is it's not there. It's kind of a beautiful bit of mathematics that happens for some discrete distributions, but doesn't apply more generally, and all the emphasis on it, well, you need to know about that, but it's misleading people.
Now, you're mentioned in Fisher's book on scientific inference in connection with the correlation coefficient example. How did your work on that transpire, and how did your correspondence with Fisher go?
There was the fiducial paper. There was one in Biometrica and one in the Annals that grew out of a talk at Stanford, an IMS meeting there in 59, 58, 59.
I was just wondering how you came to correspond with Fisher about the correlation coefficient.
Oh,
how when you were thinking about fiducial inference.
He wrote
that was just something you focused on.
He wrote me an air letter, air letters that used to exist, written on all sides on the covers, and telling them open you missed half of it. But he wrote one complimenting that article on fiducial and saying, but what about the correlation coefficient? And so we corresponded a little bit, and the correlation coefficient doesn't quite fit that group structure as it stands. Dave Sprott later showed that with other variables, chi-type variables component in there, there is location structure for r over root r 1 minus r squared and rho over root 1 minus rho squared that's latent in there. I don't think that's particularly important in the longer picture of things, but there was some of that group structure in there. So there was that, and then I corresponded with him a little bit, and there was some of the trivariate case looked at, yes. And then he wrote a few things back. I didn't pursue those particularly with him. Annie particularly followed the fiducial because once the group framework came in, so I sort of pursued the group structure, and in that group structure, the probability is space is normally a fixed error distribution, so the probabilities are part of a model that's this error space. So working from that, a lot of them got involved in that, and that's tied in a bit with the pivotal inversion, because if you have a pivotal, there's a fixed distribution there, and so does the pivotal distribution come first or the error distribution come first? If the error distribution comes first, then you have this other structure. If the pivot comes first, then you invert. But the pivotal, as you define it, sort of like is something from the original statistical model where the error is taken as primary in the other case. So sort of moving between those. George Barnard has pursued the pivotal approach, and sort of there's a lot of the thing is sort of like a change in language between an error distribution and a pivotal. But coming from the asymptotics more recently, sort of getting into the pivotals, as kind of a primary thing is sort of how you get structure there. So it's sort of like deja vu. You're back doing some of those things that you had experienced from another point of view earlier.
Well, how did the 1968 book, The Structure of Inference, come about?
It was working from the error distribution. It would be sort of like an amplification of that 59 Biometrica and the rest of it, where the error distribution is primary, and then you had transformations of that. And in that book, you inverted onto the parameter space, and that makes everybody see red. The typical frequency, this person sees red, and then the Bayesian sees red because that kind of inversion is his territory. So he doesn't want a frequentist doing it. So
I see.
There's a tussle between areas who has that. But, so that was really getting the error. That book was developing that. The later one, the inference in linear models, was largely covering the same sort of thing, but avoiding the inversions, looking at the distributions themselves, and then you could do confidence, or you can do whatever you like. If you put up something that strikes someone or others as an absolute, it brings people out of the woodwork. Like the structure of inference must have been a red flag. Not only that, the book had a kind of something red on the front, so it must have been provocative from all points of view. So more recent things, like into the asymptotics, there's nothing of that provocative nature, or nothing nearly of the same. You're sort of trying to explore something that's there.
Do you want to say anything more about the connections between structural inference and pivotal points of view?
Well, sort of like if you think of the pivotal point and the structural point of view, you think of the structural, the error distribution, the pivotal distribution, and then you sort of like the transformations in one or the inverses of the one and the other, sort of within fairly wide general, there's a notational overlap between them, but the way you think about them is quite different. And then pivotal inversion doesn't have the red flags to the same degree connected with it.
Indeed. What are your thoughts on marginalization paradoxes?
Well, they're very real, and the paper by David, Stone, and Zidek explored them in the Bayesian and the structural, and sort of more recently looking at default priors and sort of examining what can happen. The pure cases, you have a location model. I mean, they're pretty pure, but if you can't solve that, then you can't solve one of the nicest problems, so it's reasonable to think about that. And in the location case, if you do this kind of inversion and think of the Bayesian survivor function or the p-value from regular statistics, there's a 1-1 correspondence for linear parameters. And there's no problem. But if you take a parameter that's curved, in those terms of those location parameters, then you're going to have to target your prior on that parameter to get some kind of sensible correspondence between them. And the targeting in terms of asymptotics is just looking at a ratio of information determinants, one calculated for the nuisance parameter as it is, and one for the nuisance parameter relevant to the local linear parameterization. And so sort of how you shift from one to the other is pretty easy to the third order. I think that the marginalization paradoxes are connected with inversion. And if you invert and there's certain kinds of nonlinearity, then there's the problem. I think the ultimate thing that decides between them is that, well, from my point of view, more frequent is that things have to make sense frequent test wise before, let's say, by Bayesian wise. In Bayesian wise, you put a prior on it, subjective or otherwise, and you get the posterior, you get answers, and you need answers for a lot of problems as a starter, you know. So I don't really worry about that kind of marginalization paradox. I mean, how it happens is fairly clearly defined, I think.
I see. During your career, you've worked on inference and transformation models, which involves conditioning on ancillary statistics. And you've also looked at inference and exponential families, where conditioning is also important, but in that case, the conditioning is on sufficient statistics to eliminate nuisance parameters. And you've mentioned asymptotics, but could you speak in more detail about how these methodologies can be extended to handle inference for more general models?
Sort of the indications in that direction come from the asymptotics, and what form can an asymptotic, you'll accrete data and the model grows, what form can come out of it. And if you think of just first of all, a scalar parameter case, even a scalar variable case, and you start looking at the thing, you have a spectrum of what a model can be. There's sort of a meta-parameter, and one value of that meta-parameter is location, another value is exponential, and then there are other models. So it's just a one-parameter one meta-parameter that describes the difference between them. And then if you think of that in a more general context, you can think of the exponential model analysis and the location model analysis. And what you do in practice for those is quite different. If you're in an exponential model and you have big dimension, you have to come down to the dimension of the parameter. You marginalize via sufficiency. In a location model, you condition when you come down. Well, those are quite opposite kinds of things. And then when you're down to the same dimension for the variable and the parameter, and you're interested in some particular scalar parameter, in the exponential model, and you see papers on this, you condition to get rid of the nuisance parameters. Whereas in the location model, you marginalize to get rid of them. So the process in these two models are quite different. So when you go to this general case of a general model and say, how are you going to do it, you have two different paradigms for doing it. But what turns out is the paradigm that you use is the one that's in location model theory. You condition to get your dimension down, and you marginalize to get rid of the nuisance parameter. And the interesting thing is that that works in the general case and works in the location case. It winds up working in the exponential case as well, but you never think of it that way. Partly because when the two models overlap, you're in normal-like case, so conditioning and the marginalization and conditioning is kind of like the same because it's the same conditional distribution, and then a conditional p-value is a marginal p-value anyway, so the other one kind of sorts it out. So you have these two methodologies, and the thing about it is the one for the exponential model is the one that doesn't work in general. The one for exponential model is you marginalize by sufficiency and you condition to get through the nuisance parameters, and you try to chase that away from the pure nice case, and it doesn't work. You have to kind of completely switch the role. And people really don't very know much about location models. That was something, well, Fisher had a bit on it, sure, and Pittman, sure, and Verhagen, but sort of generally you talk about that and it just blank faces. And yet it's the core of how inference works. And so somewhere there are some of these gaps in terms of sort of bringing areas together, and you can try to do it, but then you have to get some fairly big picture up in imagery before you can talk about sort of the overlap between them.
Could you elucidate the connections that you alluded to earlier between inference for transformation models and inference for exponential families?
What comes out of asymptotic theory is that you condition, I'll say condition to eliminate error, and then marginalize to eliminate nuisance parameters. And this is sort of like in the nature of the structure of an asymptotic model. You look at it in terms of Taylor series, and there's certain characteristics that are present, and this is the structure that's there. You have to condition on an ancillary and then marginalize to eliminate the nuisance parameter. When you come to exponential models, and exponential models provide an example of sufficiency, and they've been around for a long time, and how you handle them as part of the traditions of the subject. And with an exponential model, or sort of more generally in a sufficiency context, you marginalize to get rid of what I would call error. With a sufficient statistic, the conditional distribution is free of the parameter. So what that conditional distribution is, you can refer to as error. It has a known distribution. So you marginalize to eliminate error, and then when you go to eliminate the nuisance parameter, the standard tool around is to condition to eliminate the nuisance parameter. So here you have asymptotic theory says to condition and then marginalize, and then the traditional theory says the reverse, to accomplish the same. So when you come to, let's say, have a pure exponential model, you're talking about doing opposite things with. And is this sort of like a paradox, or is there something wrong, or is there something not working? And it turns out all to be right, and what it really says is that what happens for an exponential model is something singular, and it can't be extended. So the way to see that is probably to think of the sufficiency context, and let S be a sufficient statistic, and then you think of the error, the conditional distribution given the sufficient statistic, call that variable t, and t given the sufficient statistic S has a distribution that's parameter free. So that's kind of the structure of sufficiency or of exponential models. So just supposing the variables are real value, just to sort of make things more easy to talk without a chalkboard or whatever, you can think of doing the following. Take the conditional distribution of t, the error, given the sufficient statistic, do a probability integral transformation of that known distribution, and get something which I'll call U with good reason, because it's going to be a uniform distribution 0, 1 given reasonable continuity. So here's a transformation of the error that puts it uniform 0, 1 subject to minimal continuity restrictions. So what you wind up with then is the uniformly distributed variable U, and then the statistic that formerly was sufficient, still is, S, and they're now statistically independent because the conditional distribution is uniform 0, 1 regardless. So you have two variables, U and S, statistically independent, and one of them is uniform. So you can flip and look at things the other way around. You can condition on the uniform variable and examine the distribution of the sufficient statistic. So that conditional distribution is the former marginal distribution. It appears as a conditional distribution given this uniformly distributed variable, and that uniformly distributed variable now has the role of an ancillary. So you look at it suddenly conditionally, and then it's equivalent to what you had marginally, but you got it into the other context. So that links the first reduction, the first steps in the two processes. Asymptotically says you condition to eliminate something, sufficiently says you marginalize. Well, when you can do both of those, they wind up being the same because of this kind of argument or extensions of it. So that sort of deals with one half of it, eliminating the error. So in a sort of nice setting, you now have a variable and a parameter of the same dimension. And then kind of recent statistical inference theory is focused on a scalar valued interest parameter. If you have a vectored valued one, you can look at the coordinates one by one in sequence. And there may be a few complications when building on that. And then if you're picking them up, we could mention it later. So in dealing with the nuisance parameter, the other aspect of it, sort of eliminating nuisance parameters, how do the two turn out to be the same? In asymptotic theory, you marginalize to eliminate nuisance parameter, and then in the exponential model you condition. Well, if you condition to eliminate the nuisance parameter, you can pick up a p-value there. It's a conditional p-value, but being a conditional p-value, it's also a marginal p-value. So what comes out of the sufficiency exponential model theory is a conditional p-value, but it's a marginal p-value, and it fits in with the asymptotic theory. So the two aspects, and they agree, but they agree because of kind of different structure. So it's kind of I'm not sure what you'd say. You have all this theory that's built up in statistics that is structured around sufficiency. An elementary math stat book would have to have a long section on sufficiency. And here, when you go to a very general context and look at the generality that you can find, a sufficiency is an anomalous condition. It depends on a conditional distribution being free of the conditioning variable. So it isn't as if it was a special case. It's a dimensionally special case. It's almost in a sense a trivial case, and so much of the attention has been focused on. Of course, that has its place with a lot of contingency cables and discrete models, which depend heavily on the exponential context. But still, so we're back to what the asymptotic theory says. What do you find when you accrete data? When you accrete data, you have to do it this other way. Not only that, it's simpler to the third order in the asymptotic sense.
Okay. What do you see the complications are in going from the case where you have a scalar parameter of interest to the case where there's a vector parameter?
Well, the asymptotic theory lets you look at the coordinates one by one, and then you get a p-value for testing each coordinate. And then I don't think there's any particularly special theory that tells you how to put those p-values together. And when you get them in sequence, you're depending on the order in which you looked at the parameters. So I don't think the theory tells you directly how to get a test that's free of the order for the vector case. In fact, it's something that some of us played around with. The sort of the feeling that came out of it, I wouldn't want to assert this, but the feeling that came out of it is you couldn't get third order. That somehow getting third order for a vector parameter that was free of the order in which you looked at the coordinates would require the kind of symmetry that you get with a normal or something like that, that it wasn't very available in general.
But going beyond the asymptotic theory, what do you see as the approach that you bring to that handling a vector parameter?
Well, I'd first sort of defer to what the asymptotic theory was indicating, because it's talking about a pattern that's in the nature of things. So if it's going to work, you have to have something that works there. So it may just say that you can't do third order for a vector case. I sort of feel that. I wouldn't want to assert it. So how are you going to handle it? Well, the fact that something depends on the coordinates. In practice, the coordinates are going to be arbitrary indexes without any physical reference. Typically, parameters, if you're really approaching a problem, are going to have some physical meaning. And when they do, you probably are going to approach them in some kind of order. There's the kind of standard problem that shows up that everyone refers to, and that's a normal distribution arbitrarily on the plane, and then you look at radial distance of its mean from the origin and then the angular departure. So you have a nice simplification, but you have certain complications that aren't present in some very simple problems. So you can think of testing radial distance, or you can think of testing angle. Once you set that radial distance and angle, there's a singular point at the origin as far as some of the things you do. So trying to force things in the neighborhood of the origin after you change coordinates that way is kind of violating sort of the role of the parameters.
To extend, you were just talking about extensions about the transformation model approach to more general families to reduce dimension by conditioning. And in transformation models, you have exact ancillaries available. For more general models, you wouldn't have exact ancillaries available for that purpose. So you need to condition on something.
Right. So you part of the way you get to look at it is to think of your observed data point, what the model looks like near the data point, and getting a first order ancillary. Actually, you can get a first derivative one very easily at that point, and that would be one step towards first order approximations.
Now, how would a derivative?
Well, it sort of gets into certain things we've been pursuing when we think of a parameter pushing a data point. If you, simple case of having a distribution on the real line, you change the parameter a little bit, the distribution is somewhere else, and you can actually think of that as a shift of the distribution. So if you retopologize your axis, the shift can be actually uniform. So related to that is talking about the velocity of a point under parameter change. So in these bigger models where you go to your observed MLE and your inference is going to be really for thetas near that, if you're thinking of moderate deviations, then you can think of a small change in the parameter and how it moves your data point in a big dimensional space. It might move it in a certain dimension. Well, you can show that that's tangent to an ancillary to the next order. And being tangent to a second order ancillary, it turns out that allows you to get third order inference for a fairly easily explained reason, so that you can get these, you get your velocity vectors, and that gives you tangents to the ancillary, and then for third order inference, all you need is first derivative properties of a model. That's one of the, well, it comes out of the saddle point, and then when you get it into statistics and say, how are you going to get these third order p-values? You're going to get the third order p-values by having the likelihood of a data point and how the likelihood changes if you wiggle your data point a little bit. And once you know the direction of the ancillary, you have to look at wiggling it in that direction, because that's sort of the conditioning. So all you need are these first derivative properties. So if you have an observed likelihood, then an observed likelihood gradient. You can think of L observed theta, and then I usually call the other one phi of theta, because it winds up being a canonical parameter of a best fitting exponential model. You only need that observed likelihood and the phi of theta, and all of third order inference sits on those. You can get approximate exponential model that agrees with that, or approximate location. Which one would you use? Well, for third order inference, they give the same result. They're free of, well, we had this spectrum from location through to exponential, and that happens in the multivariate case. And so it doesn't matter which one of the models you use, the sort of p-values are going to be the same. So there's a remarkable cancellation or disappearance of certain things, and it's in the Taylor series expansion, but it's kind of hidden, buried there, and so it's kind of exciting to see these things out. There was a C there, and actually Dave Andrews set things up in the computer algebra, calculate certain integration formulas, just to see everything laid out. And so you want the distribution up to the data point. Sure enough, the term with C and it disappears, and that's really why what happened for the saddle point happens more generally. Instead of applying it for sort of an exponential model, you can apply it to the Cauchy, and it works. And the Cauchy is as far from exponential as you could find. It works because, well, if you do this asymptotics, what you're going to be looking at doesn't depend on this, call it a C, a certain coefficient, quadratic and variable, quadratic and parameter. This disappears out of the thing. It's sort of a magic of the Taylor's series are pretty pedestrian things, pretty hard. Some people can do them better than others, like you can. But here you have this result that certain coefficients just disappear out. And I mean, it'd be nice to stop and ponder why, but the fact is they do. And then it'd be nice to get some hard theorems related to that, but the reality is there.
Now, these ancillaries you're pursuing, are they feasible to calculate?
They would be assuming that you had a pivotal quantity. If you have a scalar coordinates, independent coordinates, and a scalar parameter, you have a distribution function. The distribution function probability integral transformation is a pivotal quantity. So you have this coordinate by coordinate pivotal quantity, and I like to think of that as giving you the relationship between the variable and the parameter at certain values for each. So if you go away from the scalar case, the vector case where things are more complicated, a starting point is a pivotal quantity, and you take that pivotal quantity as somehow describing how parameter and variable were interacting with each other. And if you say, well, I'm going to take that as describing, for the moment, put it up for whatever, how the parameter and variable related coordinate by coordinate, then that predicates this ancillary. It produces the tangent vectors and produces it quite simply. All you have to do is invert a couple of Jacobian matrices. And,
I see.
And part of a program that is now implemented, and it relates to a paper Nancy, myself, and Jianrong Wu that comes out in Biometrica shortly, and that is beta alpha. Maybe if programs are beta versions, I don't know whether earlier versions are alphas or gammas, or I guess alpha as well. This earlier program is kind of a hands-on one. It'll do that calculations, do the derivatives, and for you. And so instead of sort of stumbling along, are all my multi-dimension derivatives right? Poor old Maple. I'm sure it's Maple. I think it's not Mathematica Water.
Yes,
it does the calculation flawlessly for you.
Oh, very
so
good.
So then you can get the third order p-values. They get printed out for you. And you can plot them for different values of the parameter of interest, and you get a confidence band.
Now, for the non-specialist, could you talk briefly about what you mean by first order inference and higher order inference, and why you sort of view it as important?
Well, first order results in statistics can refer to the score variable, typically, or the maximum likelihood estimate. And the score variable in most contexts is a sum of independent things, so it's asymptotically normal, so the central limit theorem comes along and gives you distributions for that. So that's a first order distributional result. When you can play with the likelihood function expansion, invert that score distribution, it gives you the distribution of the MLE. If you're working with scalar cases, and scalar case is a simple one, and start comparing the score and the MLE, they first order equivalent, but they can give horrendously different results if you take a small sample case. The other first order one that comes up is the sign likelihood ratio. There's a lot traditional likelihood ratios. So if you multiply by 2, it turns it into a chi-squared variable. And if you're in the case where it's one dimension, you take the square root and you get something that's nominally normal. That typically has much more stability and reliability, better normality and better measuring of departure. You can think of those things as measuring departure. So you have those as better measures of departure. So those are all first order, and then you have the spectrum from good to bad. And if you take some simple problems, you can use the score, and you can get horrendously goofy results, a p-value that's 13 zeros, or in the same sort of thing with an MLE. When you do the sign likelihood ratio, it's unlikely that it's going to be really goofy like that. And then some of the more recent third order results, not probably because they're third order, but because they're better structured in terms of the problem, can actually come in give, not because the theory says so, but just somehow because it was based on third order theory and somehow respects the structure of a problem, comes in with values that can wind up being distributionally very accurate and also actually provide sensible measures of departure. So you don't get this thing, like I just mentioned.
Yes.
Well, you can think of both the score and the MLE as being kind of tangent derivatives, sort of like tangent approximations to something. So if you're thinking of a function of two variables and you take a certain point and look at a tangent, it's not going to be as good as using the functional form as much as you can. So working with likelihood, you tend to pick up the functional form more as far as you can handle it. Like if you're in a problem and you have a data point, if you look at the likelihood and the model structure near that data point, you're looking at what's really there. And some of these other things are really saying, well, I'll put a certain kind of tangent at that point. And then if you walk out the tangent, some figurative sense, you're going to fall off maybe. And it's sort of, when you bring your approximations in, do you stay with as long as you can with the structure, or do you gamble?
Okay. With these approximate ancillaries you've been describing, do problems of non-uniqueness come up?
They do in a curious way. Sort of one thing you can think of, say a scalar parameter you're looking at. You go to your data point, and the theory sort of defines a second order ancillary through that point. And then you say, well, I'll go along in a kind of computational sense to somewhere along that ancillary and recalculate the ancillary on the basis of that being your data point. It's going to be a little bit different. So your ancillary that you use is going to be data dependent, and there's some things like data dependent priors that are already agitating people, but this is getting a little bit beyond that. But what you can show is to third order that those agree to the second order, and they agree sufficiently to the second order that they produce the same order result. So it becomes sort of an academic question. The ancillary isn't unique, but it doesn't matter.
In the structure of inference, and in the subsequent book, you make a case for conditioning when there are group structures. For more general models, do you actually believe in the conditioning philosophically, or is it a tool for convenient inference?
Well, it's a little bit of both, because you have your statistical model, it's big dimension, you have your data point, you go and look at the model and you say what's the structure at that point, and the structure is one of, like, in a certain direction, you variable and parameter sort of relate to each other, and then when you go to one sheaf or something to another, sort of the marginal for those is free of the parameter. So it's sort of like part of the structure. Now, whether you sort of have an absolute statement of that's kind of hard. I'm not sure, but I think it's inherent there, and somehow just how much you could pull that ancillary off purely from the expansion structure, or whether you need some of this coordinate by coordinate pull, I'm not sure. But I think it's a real part, and it's how you separate the influence of the parameter on the data. Certainly if you're a single coordinate, change the parameter distribution shifts, and if you take that as something, call it as a given, then you have a bunch of dimensions, then it applies in big dimensions. So you can think of this velocity of a point under theta change, and that almost tells you that you sort of have to look in those directions if you're going to see from a data point what the parameter might be.
Sure. You mentioned Bayesian inference and data-dependent priors. Do you want to say more about those?
Well, data-dependent priors, well, that's one step worse maybe than an ancillary. Well, I'm not sure, but fortunately there's the Box and Cox problem and the data-dependent prior that David and George put together for that, and it's pretty clear that has to be, talking with David recently in his quiet way, sort of looks, but of course the prior has to depend on the data. And I mean I feel that way, but it was just as quiet. Not only was that part of the one solution for that problem at the time, it's very much a part of his thinking. So having the prior depend on the data is sort of taking the Bayesian tool, and in the mid-50s, the work of Savage and others in the book sort of produced a lot of kind of Bayesian methodology where you can apply it to problems. You could put priors on and start to get results. And the industry, the statistical industry, had shrunk to kind of into a knot of decision theory where you're paralyzed. At the same time was the sort of Fisher direction. So those two forces or two directions are still there. Sort of to answer the Bayesian thing, you still have to get posterior probabilities, and if you're in a big dimension space, 15, 20, 100 dimensions, you just don't go and do numerical integration. You don't go and sample because you don't have the norming function and you don't have any marginal structures, so that's where the Hastings Metropolis, the MCMC has come in and allows you to sample from those distributions. I mean, there's a bit of interesting history because Keith Hastings was at Toronto, and he came into statistics. I think he was one I influenced to come into statistics, and one of the things were these structural models, the transformation parameter models. So you get a conditional distribution of the dimension of the parameter, and then you want to get p-values and the rest of it, then you have to integrate in a space the size of the dimension of the parameter. And what do? Traditional things were importance sampling. Well, naively set up an importance sampling for a problem with 10 or 15 dimensions. And I remember seeing the results coming out from the IBM cards and the rest of it. You have these weight functions, so you get your values, and suddenly this observation came along was worth 10,000 of all the previous ones you had. So the importance sampling is a nice idea, but it has to be very tightly structured. And Keith was in that kind of milieu where we're talking about, and Jeff Watson was at Toronto, so Keith went on. His thesis was on something that I think that Metropolis also did, and then the two were put together. I think Metropolis initially got credit for it, but then Keith had this work at Toronto, and then the Gibbs sampler, and then more general versions of this was a way of sampling from these distributions. So this gives the Bayesians horrendous tools to work with because they're computers that can do this thing. The MCMC allows you to you only work with one dimension at a time, and you just have to worry about whether you're going to get some sort of convergence. Interestingly, the asymptotics, as long as your Bayesian posterior is reasonably respectful, then you can get these third order values there. And I mean, you've done work on that with Martin, and then I think we have some formulas that kind of get rid of the need for nuisance parameterization, sort of build on that.
Very good. Have you thought about the use of MCMC methods to replace the asymptotic formulae?
I just think of them as a supplement too. I mean, the asymptotics are a way of checking on them. I think they're kind of tools that are available. I'm not sure how much they overlap. The asymptotic ones are reasonably simple ones in the sense that you're just calculating informations, and if you're going to do any maximum likelihood estimate having some iterative algorithm, your chances are you're going to calculate Hessians and information matrices. So the things that you have to deal with aren't that complicated. Where I think with the MCMC, it has to be there's a fair need to target it on the particular problem. I mean,
I see.
Just dimensions can change, and then what priors are you going to use? Where you can think of some of this asymptotics, you can do it without the priors, and then you can bring the priors in. One thing we've been looking at recently is how to put a subjective or communal prior on top of call it a confidence fiducial or Bayesian. And so, like you have a confidence result, then I can actually put the subjective on top of that. You can do that in a location model structure, and now it's clear that you can do that in the asymptotic context too. So it links things more closely together.
Oh, very good. You mentioned before the Cauchy distribution, and there's this example that Peter McCullough has of non-unique ancillary statistics. And I was just wondering if you have any thoughts on that.
Cauchy distribution, one of the delights is somewhere in one of the books, it's got the witch of Agnesi. I guess for a long time it's been viewed as a problem. I mean, it's mathematically really very nice, but it's got the long tails, and they're worse tails, but it's an easy one to examine long tails. Peter's result where he builds up the ancillary, very, very elegant, but I kind of part with him at one point. The transformations he uses are the linear fractional transformations on the real line. And in a practical sense, that the Cauchy distribution, it takes and folds it through plus infinity. That's because you can think of the Cauchy as being projected from, let's say, a uniform in a circle, and you could wrap around the uniform, and then when you project that, you could have a Cauchy, and the Cauchy slides through infinity, and then you can build up different ancillaries. That tends to be taking an ancillary as something very literal, like it has a fixed distribution. But then if you stop and say, what's its structure? And then you have these discontinuities because infinity is just the artificial point put in. And then it's sort of saying that there isn't a relationship between the variable and the parameter in some sense. If you think of measurement, you have a variable and a parameter. The measurement is kind of an analog for the physical thing. They're closely related.
Sure.
My remark yesterday about my 7-year-old putting up 5 fingers and 2 when asked what her age was, and I said, is that an analog answer or a digital answer? Well, we talked a little bit about digital things and analog before, so she laughed at that. So, so we're coming back to the Cauchy. It's a testing ground, but sort of when you do mathematically elegant things and then you depart from what the real structure of a problem is, then I think you depart when you roll things through infinity, because that isn't the physical thing of measuring things. Analog for something.
Okay. You also mentioned the importance of likelihood in teaching, and you've sort of been involved with the work on principles of likelihood, or principles of inference, likelihood, sufficiency, conditionality. What are your views in the state of principles of inference?
I think if you're going to schedule a talk on the foundations or on the principles, you'd be lucky to have, in a meeting, you'd be lucky to get anyone. No people aren't interested in foundations, even though in some sense, maybe because foundations became boring at some point, but it's not something that's in everybody's mind. They don't. But back when Birnbaum did that, the meeting in New York City, I heard him talk that the atmosphere is electric. I mean, here, sufficiency, conditionality, likelihood, and relations between them, some things people believed in and they didn't, and then there's certain equivalences, and it just violated what people believed in, and there was this, you've put something up that's, I mentioned that before, something that's up like an absolute, and it brings people out. If it's diffuse and undefined, like with confidence, you can have pivotal quantities all over the brain and get confidence intervals that do bizarre things, open-ended intervals, you can get empty interval, in a case that could be 100% confidence interval. Nobody even cares about that. But you come along with something that has some sort of bigger claim, then it brings out, maybe it's the latent mathematician, I'm going to get it. They want to just, there's this sort of that meeting was, and if I remember correctly, Neyman got up and spoke for 30 minutes on the decision theory model. And I mean, almost everybody there had been through decision theory, and it wasn't really appropriate, but it was just sort of like scolding Ellen for doing this kind of thing. But what he did was really very fundamental. He brought set theoretical notions in here about implications between the use of these principles, and there was the connection, sufficiency and conditionality, implied likelihood. Well, Mike Evans, George Monette, and I sort of showed later that conditionality alone implied likelihood. So if you believe in conditioning, then you're going to get the likelihood principle. Well, only if you sort of allow the conditioning to be quite arbitrary without some sort of structure. And part of proving that conditional likelihood was what we call cross-embedding two models. And in general context, that means you can sort of like pull things apart, piece them together. So if you bring in some kind of connections or continuity or stuff, you can't do that. So you have these proofs, they're in a particular case, but it brings people to focus on those. I don't think anybody would really, I mean, people will come back and have further thoughts on that and other integrating things, and there are people working on them currently, and I think I think that's good. There's a tendency to get lost in the mathematics of it rather than sort of what does this real mean for application. I don't believe that conditional implies likelihood, but there is that proof in a certain context. And conditioning, you should condition. What are you going to condition on? An ancillary? Where are you going to get the ancillary? It must make some sort of sense. What's your reference set? Fisher's idea of reference set. That's kind of something that's flowed. And then conditional model, marginal model, they're all things that need attention, but it involves kind of big chunks of structure, so you can't just sort of carve out a little area and go grab it.
I see. You mentioned your daughter. And you actually have 7 daughters. And
7 daughters, right?
Some of them are involved in the mathematical sciences. And I was wondering if, reflecting back, you could sort of pinpoint any ways that you were able to foster their interests or abilities in that direction.
Well, maybe they were watching somebody who's pretty fervently involved or committed with mathematics. So it kind of enticed them into it. I think it was the carrot rather than sort of like environmental influences they see. The 3 middle daughters all went into mathematics, 1 Princeton degree, 2 Stanford degrees. They're all in analysis, symplectic geometry, differential geometry, and they all had some exposure to statistics, but never went in that direction. The oldest daughter married Dennis Broad, a cellist, and so she's very much involved in the music world. And her younger sister, Dady, we had some connection with statistics when at McMaster, but sort of languages and French, and who can say about 4-year-old and 7-year-olds.
That's right.
But if they can laugh about analog and digital when they're both the same, maybe that was set up too much.
Now, talking about analysis and symplectic geometry, your work has sort of a unique flavor to it and a very characteristic style. And I was wondering how that has developed over the years and how you found it useful.
Well, I'm not sure that I'm aware of the style. I'm aware sometimes that people are critical of the style or faulted or something, or to some degree maybe it's non-standard. It's sort of how you think of things, and often think of geometry like you can see something and then you have to get the mathematics together that describes that, and that putting together may be hard, but they sort of like the conception initially of those things, that's a different kind of mental kind of anguish, until you can feel it. And so how that it sort of, can you really feel differentials? I like to think of differentials all the time. I mean, differentials are are credible, from a certain point of view, but they're when have I written down a chi-squared distribution without putting d chi-squared over 2, because it has to be there. You don't want to be carrying a lot of constants around. That one's stuck to the chi-squared, why not leave it there? Little things like that you can follow you through into other things and mean that you're doing things differently from other people and perplexing them perhaps at times, maybe irritating them at other times.
Yes.
Not by intention, just by some sort of default.
Did this grow in part from some aspect of your training or particular courses or reading you did as a student?
Well, maybe in the sense of sort of wanting to see things from your own point of view and then finding ways to see them, or putting your own way together that satisfied you, rather than spending the time sort of always sort of like seeing sort of what the standard approaches were. I mean, the other side of that is a lot of things have been done very well, and if you shortchange yourself on the background there, then it has an effect on the same thing. If you shortchange yourself on pursuing certain things, it can have a negative effect too. So I don't know that there's a conscious thing. Over time you feel some reinforcement to pursuing things where even though the people said it wouldn't work, you felt it would, and then you do find later that it works, so you get some kind of reinforcement back for pursuing something that maybe a lot of other people would say would not be feasible.
Now, you're seeming very optimistic about the state of inference and extending the sorts of things you've been looking at throughout your career in new directions. What are the problems that are currently appealing to you or enticing you?
Well, huge areas of statistics that involve discrete data, counts, contingency tables, and the asymptotic says something about that, but some of these recent methods, particularly what's in that current Biometrica paper, are really working with a continuous variable.
Sure.
So extending it to this other means getting something that you can approximate by a continuous variable in some practical sense, or doing certain other things. So that's it. I think it's not something that's going to snap in place with a few aberrant thoughts at some point, but I think it's a very important area and one that we plan to pursue as time allows.
Well done. Thanks so much for giving us these interesting and valuable perspectives on your impressive career. Thanks for coming in today.
Well, thank you very much, Tom. It's great interview.